Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain.
Today, we are super pleased to have Dr. Jonathan McDowell on as a guest. During work hours, Dr. McDowell is an astrophysicist at the Center for Astrophysics, Harvard and Smithsonian. And while that's amazing, the real reason we have him here is he is the orbital police. For decades, McDowell has tracked orbiting objects and helped plot out the orbits of random objects, including Elon Musk's solar orbiting Tesla. Before we get to that interview, though, let's take a look at the news.
In today's first story, we have a headline that made me cringe. The good folks at the International Center for Radio Astronomy Research put out a release titled, "Astronomers Just Got Better at Finding Bright Black Holes." Folks, black holes, by definition, emit no light and cannot be bright. That said, the headline "Bright Black Holes" is way more click-worthy than bright active galactic nuclei. And since active galactic nuclei contain a black hole, we're gonna cringe a bit and just move on with the story. Deep in the hearts of some massive galaxies, disks of material can be seen spiraling in towards their central supermassive black hole. These disks can become hot enough and dense enough to glow brighter than the entire rest of the galaxy around them. In a paper in Monthly Notices of the Royal Astronomical Society with first author Jessica Thorne, researchers describe a new image analysis algorithm that can take data from multiple telescopes and use fit models of the host galaxy and active black hole to find out if an active black hole is needed to explain the observed light. According to Thorne, we can identify these active black holes and look at how much light they're emitting, but also measure the properties of the galaxy it is in at the same time. By doing both at once, we can have a better idea of exactly how the black hole is impacting its host galaxy. This software can be used on existing catalogs, and the team is already directing their software at the Gamma and Devils surveys. Those are both acronyms. This gives them toward 1 million systems to search for active black holes and the glowing disks that surround them. We look forward to seeing what they find.
Annoyingly, some of the most impactful things in our universe just can't be directly observed. Ignoring the giant pillars of dark matter and dark energy still leaves us with those same don't emit light black holes. Beyond affecting the evolution of the stars they may evolve with, or the evolution of galaxies they may sit in the heart of, well, it turns out supermassive black holes can also hollow out the cores of galaxy clusters. Researchers compared images from the Hubble Space Telescope, which shows us where stars and nebulae are located, with data from the Chandra X-ray Observatory, which shows the distribution of hot gas. Much to everyone's surprise, the X-ray images showed massive cavities to either side of the cluster's central galaxy and lesser cavities above and below. In a new paper in the astrophysical journal Letters, researchers led by Francesco Ubertosi describe how this kind of a structure could be blown in the intra-cluster gas by a pair of actively feeding supermassive black holes with perpendicular jets. According to study author Miriam Giddy, while we think supermassive black holes can form binary systems, it is extremely rare that both of them are observed in an active phase. In this sense, the discovery of two close active black holes inflating cavities in this cluster is extraordinary. Along with the cavities seen in X-rays, additional data from the Very Large Array shows two pairs of jets aligned with the sets of cavities. If the cavities and jets are from two supermassive black holes, they are the closest pair found so far. But before you go assuming that all these hoof prints indicate two horses are hanging out, there is a zebra we'd like to bring to your attention. It is possible, maybe, that one supermassive black hole could be responsible for this system all by itself if it somehow flipped rapidly. How you rapidly rotate an object many million solar masses in size, Well, that's a problem for theorists. For now, just know that apparently the jets associated with supermassive black holes can blow epic bubbles.
A lot of structures in our universe are the result of jets, collisions, and shock waves. This leads to areas of compressed material, and this compressed material can be the perfect place for stars to form. Enter the molecular cloud G0.253 plus 0.016, aka the brick. This particular chunk of dense material lurks towards the core of our galaxy, and it generally appears as a dark blob against the bright glow of the Milky Way's central molecular zone. Initial observations showed no star formation, but researcher Jonathan Henshaw remarks, when investigating the gas motion of the brick, we find one component that stands out. That substructure, confined to a narrow range of velocities, resembles a crescent-shaped arc. And in astronomy, when you see an arc, it often means something is blowing a bubble. After measuring motions in the bubble, the team worked backwards to figure out how long it had been growing and came up with a few 100,000 years. In the lifetime of a star, that is the blink of an eye. Henshaw further explains, we explored several plausible scenarios that may account for an expanding envelope forming the arc. Comparing predictions from theory to our observations, we found that the stellar wind from a massive star of about 20 solar masses is likely the dominant mechanism. Stars don't form in isolation, and these observations hint at a star cluster coming into being in this brick of a cloud. What today appears as a dark smudge will someday shine with the light of hundreds of stars. If the JWST launches, its long wavelength capabilities may let us peer into the dust and watch this new system being born. If. In the latest JWST news, the presser to talk about when it will be launched was delayed. Yes, folks, the info on when the delayed telescope will be launched has also been delayed. After the break, we'll be back to discuss Pluto's remarkable geology. Stay tuned. Back in 2015, the New Horizons spacecraft showed us Pluto looks nothing like anyone imagined. The most iconic feature on this distant world is a heart-shaped plane named Sputnik Planitia. This feature, like Texas, is slightly bigger than France. Looked at closely, Pluto's heart is made of polygons of nitrogen ice. This shape in general is associated with convection, but explaining how an icy plane convects like oil in a hot pan, that has been a challenge. Researcher Adrienne Morrison explains, we know that the surface of the ice exhibits remarkable polygonal features formed by thermal convection in the nitrogen ice, constantly organizing and renewing the surface of the ice. However, there remained questions behind just how this process could occur. Based on the lack of craters, Sputnik Planitia appears to be about 40,000 years old. To put that in perspective, Neanderthals had just gone extinct and Homo sapiens were settling Australia when this giant crater was formed. This means we aren't seeing the legacy of some ancient convection. We are seeing a modern process shaping a geologically active world. That's another thing that wasn't expected. We didn't think Pluto would be geologically active. It is too tiny to have held on to much internal heat left over from its formation, and it takes heat to drive activity. As put by Morrison, New Horizons showed that Pluto is still geologically active despite being far away from the sun and having limited internal energy sources. This included at Sputnik Planitia, where the surface conditions allow the gaseous nitrogen in its atmosphere to coexist with solid nitrogen. Over the past half decade, folks have put forward a lot of possibilities, including tidal heating from Chiron, a core rich in radioactive materials, and residual heat from impacts, like the one that formed the plane in question. But these explanations may not be necessary. In a new paper in Nature, Morrison points out that models show the ability of nitrogen to go from solid to gas as it sublimates at Pluto may be enough to drive the convection. Numerical models based on sublimation are able to reproduce the New Horizons observations, including the size of the polygons, their topography, and even their surface velocities. Nitrogen, it alone may be able to explain at least this one heart-shaped mystery of Pluto. Since flying past Pluto in 2015, New Horizons has continued its journey outwards. And in April, it passed the 50 AU mark, putting it 50 times the distance of the Earth from the Sun. New Horizons' mission is not yet over, and there is enough fuel and power remaining for the little spacecraft to visit at least one more target, if one can just be found. The New Horizons team used the Subaru telescope to search for targets last May. If that data provides no targets, all hope is not lost. The Vera Rubin Observatory offers new promise, and since it is on the ground, we know it will be completed and functional at some point in the future. After the break, we're going to be back to talk satellites that have launched with Dr. Jonathan McDowell. Stay tuned.
Joining us now is Dr. Jonathan McDowell. McDowell is an astrophysicist at the Center for Astrophysics, Harvard and Smithsonian by day, but on Twitter, he is known as Planet 4589, and he is also the Orbital Police. Thank you for joining us today, Dr. McDowell, and welcome.
Good to be here. Thank you.
So, first off, what inspired you to get into space and become an astronomer?
Well, there were a couple different paths for me. There was growing up in the age of Apollo. I was inspired by the thought of people walking on another world. How insane is that? That blew my mind, and so I wanted to be part of that. And then there was a separate thread which was more philosophical on, what is this world? Where do we all come from? How did it begin? That got me into cosmology at an early age, and so that drove me on a path of wanting to do research in the origins of the universe and things like that. And then I guess a third path was that math was about the only thing I was good at, so I might as well go with it.
So, what is something that you think is really important about the work that you've done that people don't know yet?
Ooh, that's a hard one. Let's see. What's important? I mean, so we can talk about my astronomy work or my space work. I think for the space work, the important thing that I've done that isn't out yet really is the research I've done on where stuff is in deep space, because I've been looking at the orbits of planetary probes. And people may not realize that although the Space Force tracks the orbits of satellites in Earth orbit, they don't care once it gets well beyond geostationary orbit. And so it's no one's job to keep track of where all the junk is in orbit around the sun. And so I've made that my personal challenge. And
what sorts of spacecraft are we talking about here?
Well, so there are sort of abandoned Mars probes and things like that, but also the rocket stages that put them there. The instrument covers on the mass spectrometer from Cassini that it popped off as it passed Venus and things like that. And so there's all kinds of stuff. So I have a catalog of about over 1,000 objects now that are in deep space, most of which are not in the regular satellite catalog. And so I'm doing the harder work now modeling their orbits and trying to figure out what we can say about where they are now. And so that's my passion project on the side when I'm not hunting for black holes. And so in my astronomy life, people who just know me as the orbital police may not know that one of my I've really had two threads in recent years. One is in my role as a member of the Chandra Space Telescope team. And my mission has been to make X-ray astronomy less arcane and more accessible. And there was sort of a feeling, I think, in the astronomy community that X-ray astronomers were like, ooh, X-ray astronomy is hard. It's not for you regular astronomers. If you want to work on it, you better work with one of us because we're the secret priesthood, right? And I'm trying to get the community past that and go, no, X-ray astronomy is for everyone. We understand what we're doing now. It's been around for 50 years, and so we're going to give you proper documentation and proper training to be able to do X-ray astronomy yourself. And that will broaden our user base and hopefully broaden the chance that we eventually get a successor to the Chandra Space Telescope. And so that's a cause that's dear to my heart. And otherwise, I'm interested in what weird objects can tell us about supermassive black holes. And I've always had this interest in quasars because they're ridiculous, and so what people, my selling point for quasars, right, is if you look at the sun, right, solar energy is the Earth intercepts a tiny fraction of the energy coming out of the sun. And the total energy coming out of the sun is 0.1% of the mass of the sun turned into energy by E equals mc squared over a 10 billion year period. And that's enough to generate, that 0.1% over 10 billion years is enough to generate all the solar energy ever, right? And so in quasar, you take 100% of the mass of the sun and E equals mc squared it into energy every year. So that gives you some feel for how much brighter a quasar, how much more energetic a quasar is than our sun. And so they're just ludicrous objects, and I want to understand more about them.
That sounds fascinating, and I definitely want to bring you back and talk about some of that research specifically. We're going to take a quick break, and then we're going to be back, and we're going to talk to you a little bit about some of the current space constellations and orbital mechanics that you work on. So stay tuned, everybody. We'll be right back. Welcome back. Once again, with me today is Dr. Jonathan McDowell of the Harvard-Smithsonian Center for Astrophysics, but also from Twitter, where he is known somewhat sillily, I suppose, as the orbital police. And he calculates the orbits of lots of different objects around Earth and in our solar system. So thank you again for joining us. One of the things that I think we really want to talk to you about was the Russia test, the ASAT missile test in November. You were one of the first people to publicly connect the dots of what ended up becoming a major news event. How did that come about for you? What happened that sparked that for you?
Right. So we heard when I woke up that morning, we heard that the astronauts have been told to take shelter from a debris cloud that they were passing through, and that was very unusual. It's not that unusual. I mean, a couple times a year that they get told we've got to do a maneuver to avoid a debris object, some piece of space debris that's coming a little too close to the International Space Station. But a debris cloud's a little different. That immediately suggested that there's a recent event that they haven't yet identified all the individual objects, and indeed, a month later, they've now finally got the first 500 cataloged, but probably a few thousand more to track down, and so there's still this risk of things whizzing around that you don't know where they are.
It's still really important, and it still became a massive news story that we
For
covered
sure.
here several times, in fact, and obviously still covering. So thank you for coming and talking to us about it and for letting us know. I want to have you back on the show again because we have so many questions and there's so many things to talk to you about, but
Sure.
that was kind of the main one. So thank you, Dr. McDowell, for joining us today.
You're welcome.
This has been The Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.